students, in this class, let us discuss the simplified hybrid model. In the last class, we have discussed the exact model for different configurations. So, now let us explain the importance of the simplified hybrid model by taking the exact model first. So, this is the common emitter configuration, emitter is grounded, and this is the H parameter model for CE configuration. You have connected source at the input side and taking the output at the load. So, for this configuration already we have calculated the current gain, input resistance, voltage gain, output admittance in the last class. Now, this exact model can be converted into a simplified approximate model. It is an exact model because you are considering all the 4 H parameters. Now, I would like to consider only 2 H parameters out of these 4. Then the exact model is going to be an approximate model. So, what are the things can be neglected here? If you neglect this voltage source in the input side and the HOE from the output side, then whatever that is remaining is an approximate model. So, out of these 4 H parameters, we are neglecting the effect of HRE as well as HOE. But if you neglect like this, the results may be changed by some percentage. So, if that percentage is negligible, then definitely you can use it. But that percentage is negligible whenever one condition is satisfied. What is that condition? That condition is HOE into RL should be less than 0.1. This is the most important condition that is required to use your approximate model from exact model. That means, if you want to neglect the effect of this voltage source on this HOE, this condition is going to be satisfied. Then convert this exact model into approximate model. So, draw the approximate model circuit here. So, the approximate model means you are having only 2 H parameters in the approximate model. So, if you take this circuit, simply you can write down HIE, this is HIE, and this is totally grounded because HRE is not there, and HFE times IB, this is HFE times IB, and HO is also not there, HO is also not there. So, this is the output voltage, this is RL, and the current through this one is IL, output current is IC. Okay. So, in the output side very simple, HO is neglected, only one current source is remaining here, and in the input side you are having only HIE, this will not be there. So, this is HIE, the input current is IB. So, as usual you connect the sources. What are the sources? At the input you have to connect the source, a source with a source resistance. So, this is Vs in series with the resistance Rs. So, this is HIE and this HFE times IB, and here you have connected already RL like this, RL. Now, once the circuit is available, happily you can calculate the current gain. So, what is the current gain here? Current gain AI is equal to output current by input current. Output current is IL by input current is IB. IL by IB. What is this IL? Minus IC. So, minus IC by IB. This is the current gain. So, what is IC here? Minus IC means this current only. So, HFE times IB minus into HFE times IB divided by IB. IB and IB will be cancelled. The result is minus HFE. It is an approximate model. In the approximate model, what you have done? You have neglected the effect of HRE and HOE, provided this condition is satisfied. HOE into RL should be less than 0.1. Then only it is a valid model. Otherwise, you are going to get the errors. Large deviation will be there in the results. So, that's the reason it is to be satisfied to use your approximate model. So, this is the approximate model. Now, already for the exact model, you know this current gain. Just see here. This is the current gain for the exact model. This is the current gain AI is equal to minus HFE by 1 plus HO into RL. So in this exact model, what you have done? This HO is not there. You remove this, then AI is equal to minus HFE. The same thing you got here. AI is equal to minus HFE. So it is a simple way of getting this result. So what is the input resistance Ri? Input resistance Ri is equal to, input resistance means you are seeing from this place. This is the input resistance. So this is the voltage VBE. So VBE by IB. So you can say that input resistance Ri is equal to VBE by IB. VBE by IB means very simple. Just by seeing this you can understand. VBE by IB means only HIE. So your answer is HIE. So once you get Ri and AI, AV automatically you can calculate what is AV. AV is equal to AI into RL divided by Ri. So what is AV? AV is equal to, AI means current gain. How much you got it? Minus HFE into RL divided by, what is Ri? Ri means HIE. How simple it is? You got the voltage gain. Here also you can see this. Ri is equal to HIE plus AI into HRE plus RL for common emitter configuration. Here in the approximate model, HRE is not there. Put 0 here, then Ri is equal to HIE. You got the same result. Ri is equal to HIE. Ri is equal to HIE. So that's why it is an approximate model. Approximate model means you are not considering the effect of reverse voltage source as well as your HO. Now, I would like to tell you how to calculate this remaining parameters by taking this approximate model. So, one more thing is friends, if you observe this figure, this is an emitter, this is a common emitter, and this is base and this is collector. Listen carefully, collector. There is always a resistance between base and emitter, and a current source between the collector and emitter pointing towards emitter. So, if you observe it, this particular fashion is a simplified hybrid model. This model you have to use it. So, for clarity purpose, just I am drawing here. If you are taking the three terminals here, one is the base and other one is the collector, and this is the emitter. Emitter is grounded. This is grounded here. Between the base and emitter, you are having HIE. So HIE. This is HIE. And the current IB is actually flowing through this IB. And from between the collector and emitter, there is a current source. So this is the current source between the collector and emitter, pointing towards emitter. So it is pointing towards emitter. What is its value? HFE times IB. HFE times IB. This particular fashion, this particular diagram can be used for any type of configuration. Not only in the common emitter, in common collector, in common base also, you can use this. This is called as your simplified hybrid model. This is the simplified hybrid model. So that is the reason, understand it very clearly. This simplified hybrid model can be used for common collector as well as common base configurations also. It is evolved from the common emitter model, but it is very easy to use this in other configurations. That analysis will be very easy whenever you are using this particular model. That model is simplified hybrid model. So your approximate model of your CE configuration is nothing but your simplified hybrid model. So this is the simplified hybrid model. Already we have calculated current gain, input resistance and voltage gain. So now we are going to calculate what is the output admittance, because for any configuration, for any amplifier, you have to calculate current gain, input resistance, voltage gain, output admittance, current gain with the source, voltage gain with the source also. Now let us see how you are calculating the output admittance for this circuit. Okay. So whenever you are calculating the admittance, in the last class I already told you, output admittance Y0 is equal to output current by output voltage IC by VCE, when when the internal sources are set equal to 0, then Vs is equal to 0. Therefore, Y0 is equal to, what is IC? IC is the current in the output circuit. This IC is nothing but HFE times IB. So, HFE times IB divided by VCE when Vs is equal to 0. So, in the input circuit, when Vs is equal to 0, whenever the input source is set equal to 0, then you can write down the KVL here. That KVL is IB into Rs plus HIA is equal to 0. Rs plus HI is equal to 0. Therefore, automatically IB is also equal to 0. So, from the input circuit it is concluded that IB is equal to 0. So, therefore, Y0 is equal to 0 because IB is equal to 0 here. So, if Y0 is equal to 0, then R0 is equal to 1 by Y0. Output impedance is equal to 1 by Y0 that is equal to 1 by 0 is equal to infinity. So, the output admittance is infinity. Very simple. Without calculation also you can tell the same result. It is a current source. Current source is always having a resistance in parallel with this. In parallel you are having an infinite resistance. That's why it is open circuited. In the exact model you are having some HO resistance here. But here as you are not in a position to see it, it means it is open circuited, means infinite resistance. So, your admittance is infinite here. So, that is why Y0 is equal to 0. Y0 is equal to 0 and R0 is equal to infinite. So, what is R0? R0 means you are seeing from this place. This is R0. If you are seeing from this place, then let it be R0 dash. This R0 dash is equal to R0 in parallel with RL. So, R0 is infinite. Infinity resistance in parallel with RL means lowest resistance. That's why it is called RL. So, R0 dash is equal to R0 in parallel with RL. What is R0? Infinity. Infinity in parallel with RL means it is approximately equal to RL only. So, this way you are going to calculate your output admittance. So, for this circuit immediately we can say the output admittance is equal to 0. So, the same thing also you can calculate here from the exact model. What is Y0 for the exact model? HO minus HF HR by HI plus RS. So, for the common emitter configuration HOE, HFE, HRE, HIE. So, in the approximate model what is HRE? 0. So, HOE 0. So, these two terms are not there, then Y0 is equal to 0. The same thing you got here, Y0 is equal to 0. So, this Y0 is equal to 0 is indicating that the output resistance is infinite, because indirectly whatever the current source you are getting here is an ideal current source. Ideal current source is always having an infinite resistance. So, this way you have to calculate the current gain, input resistance, voltage gain, input resistance and output admittance for the common emitter configuration. This is the simplified hybrid model for your common emitter configuration. Now, let us apply this simplified hybrid model. What do you mean by simplified hybrid model? Between the base and emitter always you are using a resistance HIE, and between the collector and emitter you are using HFE times IB, it is a current source. The same circuit can be used for any type of configuration. Even though it is given for the common emitter here, it can be used for common base or common collector configuration. So, now let us see how to calculate all these parameters for our common collector configuration, and which is also called as an emitter follower. Let us do the analysis of this emitter follower common collector configuration using simplified hybrid model. If you take this circuit, immediately you can understand it is common collector configuration because you are taking the output at the emitter. If you take the output at the emitter, it is common collector configuration. If you take the output at the collector, it is common emitter configuration. So, it is common collector configuration. If you want to do the analysis of this transistor should be replaced with your simplified hybrid model. So, first of all, try to convert this circuit into hybrid model. So, what is the input for this? Input is base terminal, output is emitter. and collector is common for both input and output, as it is a common collector configuration. Using the simplified hybrid model between the base and emitter, you are having HIE. So draw the circuit HIE, and the current through this HIE is IB. Between the emitter and collector, you are having a current source. The current source is pointing towards emitter. So that's why it is up arrow. It is. This is HFE times IB. And the load resistance is here. Between the emitter and the ground. So this is emitter and this is ground. You are having a load resistance RL. And through the RL, let us say the current through this one is IL. The emitter current is the output current IE. And the input current is the base current. And between the base and this ground, you are connecting a voltage source in series with the resistance. So you can say this is RS and the voltage source VS. This is the VS and RS. Okay. So now this is the circuit. Definitely within no time you can analyze this circuit, because the circuit is totally transformed into the simplified hybrid model. So for this circuit now, let us calculate what is the current gain. So what is the current gain here? Current gain AI is equal to IL by IB. This is IB, input current IB. What is IL here? IL and IE are opposite directions. So minus IE by IB. Now what is this IE? So if you are applying the KCL at this point, IB is coming in this direction, HFE times IB is coming in this direction. Definitely they will go in this direction opposite to IE. So IE will be negative of these two things. So if you calculate the current gain AI is equal to minus IE by IB. So that is minus, what is IE? Minus of, because IE and these two things are in the opposite direction. So this is equal to, IE is equal to IB plus HFE times IB. That means 1 plus HFE times IB, that too in the reverse direction. So that is positive. Divided by IB. IB and I will be cancelled. So that will be equal to 1 plus HFE. So what is the current gain AI for the CC? 1 plus HFE. Exactly like this, you are going to calculate what is the input resistance for this. What is the input resistance? What are the input terminals here? Base and collector. So from this point you have to see what is the input resistance RI. RI is nothing but the ratio of, this is VBC, okay? This is plus minus, this is VBC by IB. So if you want VBC by IB, just write the KVL in this path, VBC, HI times IB plus some current into this resistance RL. So what it will be? It will be RI is equal to, VBC is equal to, you can say HI times IB plus RL into, what is the current flowing through this? IB and HFE times IB, they can sum up here, they can come in this direction. So 1 plus HFE times IB. Okay. So you take the IB to this side. So VBC by IB is nothing but your input resistance is equal to HIE plus 1 plus HFE times RL. So this is the input resistance for your common collector configuration. So you got the current gain AI is equal to 1 plus HFE. So AI is equal to 1 plus HFE, and you got the input resistance also. This is the input resistance. Once you get the current gain and input resistance, it is very easy to calculate your voltage gain. What is the voltage gain formula? Voltage gain AV is equal to AI into RL divided by RI. Therefore, that is equal to AB is equal to, what is AI? AI you got it here. This is 1 plus HFE into RL divided by, what is RI for this? RI is HIE plus 1 plus HFE times RL. This is nothing but your voltage gain expression. This is the voltage gain expression, you got it. So you got current gain, input resistance and voltage gain. Now it is our duty to tell you what is the output admittance. So now we are going to calculate the output admittance, but you see in this analysis also you are using the common emitter configuration representation only. So I told you very clearly, whether it is a CB or a CE or a CC, you use this simplified hybrid model for the analysis. So this way you are going to analyze your common collector configuration, which is also called as an emitter follower. Why it is called an emitter follower? Emitter follower means the output is emitter here. The output always follows the input. That means voltage gain AV is equal to 1. Voltage gain AV is equal to 1. The output follows input, that's why it is called as an emitter follower. AV is equal to 1. And the common collector configuration or otherwise emitter follower is same. Yeah, the output follows the input, it is called as an emitter follower. For this, the voltage gain is equal to 1. But the current gain of the common collector configuration is very high. So I will tell you at the end what are the advantages of the common collector configuration also. Now we would like to calculate what is the output admittance for this circuit. Now we are going to calculate the last parameter, output admittance. Output admittance Y0 is equal to output current by, what is the output current here? IE by output voltage VEC at Vs is equal to 0. Now if you observe this circuit is having a dependent source HFE times IB and independent source. So in order to calculate this current and voltage, you have to use a different procedure here. So let us say that this is the load resistance RL. If RL is removed, whatever the voltage you are seeing here is open circuit voltage. Let us say, what is the open circuit voltage VOC? VOC is equal to, if it is open circuited, then whatever the voltage that is there, this will be here. The same voltage will be Vs. So open circuit voltage is Vs. Short circuit current I is equal to, what is the short circuit current? If you short it like this is the load is shorted, totally shorted. This current will come in this short circuit and IB also will come in the short circuit. So what is the total current here? IB plus HFE times IB. So 1 plus HFE times IB is the short circuit current that is entering into this. So I is equal to 1 plus HFE times IB. What is IB? IB means base current. Base current in this one. What is the base current here? Vs by Rs plus HI. Rs plus HIE. So IB is equal to Vs by Rs plus HIE. I want I by Vs. I is the short circuit current. Vs is a open circuit voltage. So I by Vs is equal to 1 plus HFE divided by 1 Rs plus HIE. So this is the expression for your admittance Y0. So whenever the circuit is having both dependent and independent sources, this is the dependent source and it is independent sources. From our network analysis, already it is known that you have to find out the short circuit current through the load resistance and the open circuit voltage by removing this. So I by Vs is nothing but Y0. So it is a admittance. Then automatically what is R0? R0 is equal to 1 by Y0. Reciprocal of this. So that is equal to Rs plus HIE divided by 1 plus HFE is the output resistance R0 for our common collector configuration. The common collector configuration is also called as an emitter follower. Generally, there are so many applications of this common collector configuration. Why? Because if you see the features of the CC, RI is very high. Voltage gain is unity, but current gain is more. R naught is very low. R naught is very low. That is the reason if you use this CC as a last stage of the amplifier, it is very easy to match the loudspeakers. Used as a buffer, as a latch, you can use your common collector configuration. It increases the power level of the signal. That is the reason I am telling you. Whenever you are going for the stereos, if you want the more sound, up to the last stage, there will be a cascading of common emitter configurations. Common emitter you can use in a sequence for getting the amplification. But the last stage should be common collector, because it is required to enhance the strength of the signal, and it can be used as a matching device for the circuit, for the amplifier, and as well as your loudspeaker. That is the reason the last stage of your amplifier should be common collector configuration. So this is the way of actually analyzing the circuits using the H parameters, that too with the simplified hybrid model. Simplified hybrid model means it is a model which consists of one resistance and one current source. Resistance is in between base and emitter, and current source is in between collector and emitter, pointing towards emitter. So you can calculate any type of the parameters if you know the analysis like this. I hope you understood the analysis of the emitter follower, that is common collector configuration, very clearly. Okay, thank you.